Hello young people, this is our last Unit 1.1 asynchronous video. Hope you're getting all this in your notes. We're shifting gears a little bit, but not too much. Scientists often look for changes in systems. We started with a phenomenon, coral bleaching for example, and we look at how coral fits into a system, and we look for changes in the system that could trigger that coral bleaching. But the way science works is with evidence. This is the fundamental foundation of science. If there's no evidence, you got nothing. I'm going to tell you a thing. It's called Occam's razor, Occams, razor, like you shave with. And Occam's razor is actually a tenet of philosophy. And Occam's razor tells us that the simplest explanation is the best one. And that is a fundamental truth of science as well. We take our evidence, we take our observations and our inferences, and we compile it, we put it together, and the simplest explanation that can explain all of our evidence is the best one. And that's the way science works. Thank you for coming to my TED Talk. No, just kidding. Let's have a couple examples here. From our textbook, banded iron formations. It's a sedimentary rock. It's a sedimentary rock means it's made up of sediment at the bottom of the ocean floor. And that sediment piles up, and eventually it squishes together and forms a rock. Now, banded iron formations are special. They're dated to be about 2.5 billion with a B years old, which is very old. It's hard to find rocks that old on the surface of the earth anymore as in, in the last couple billion years. It's hard to find rocks that old. And the thing that's interesting about these banded iron formations is that 2.5 billion years ago, they were forming everywhere, all over the world. And after 2.5 billion years, more recently, they've never formed again. So what would we call that? We would call that a phenomenon. It's a phenomenon. We've got these rocks with these very distinctive layers of iron. And that iron has, it's oxidized in a way that only happens with the water. Now here's the interesting thing. Well, hold on. It's oxidized in a way that only happens underwater. As a earth scientist, what do I want to do? I want to take my evidence that I have, then I want to find the simplest explanation that explains all of that evidence. So let's take some evidence here. Well, what evidence do we have? We've got that the rock is 2.5 billion years old. We've got the evidence that that rock formed on the bottom of the ocean. We've got evidence, I'm not going to go into it, but it's well established that those grains of iron that got squished together into the rock that formed on the bottom of the ocean, they actually came from the land. They came from the continents, and they made it to the ocean floor and got turned into a rock. Okay, so there's our evidence. Now, what do we know? What can we observe today about how tiny grains of stuff from the land gets to the ocean floor? You probably have an idea. What washes things out to the ocean? Well, rivers wash things out to the ocean. How does things get into the river? Well, it's eroded from a rock, it turns into a smaller piece of sediment, it gets into the water takes it to the ocean, it gets dropped on the ocean floor. If we know how sediment gets from the land to the ocean today, we can infer, we can assume that that's how sediment got from the land to the ocean 2.5 billion years ago. Rivers flow downhill. They've flowed downhill always. We can assume that to be the case as well. And the other piece of evidence that we have is how iron, that same iron, those same iron grains, how they behave today. And if I have one of those grains of iron today and I expose it to the air, it's going to rust immediately. Immediately in geologic terms. It's going to rust very quickly. Certainly it's going to rust faster than the time it takes to get it from the land to the bottom of the ocean. And it's going to rust because of being exposed to oxygen in the air, oxygen in our atmosphere. So we've got all the evidence we need to use Occam's razor to come to a very simple conclusion. We've got 2.5 billion year old rocks that form a pattern that we don't see in anything younger than that. There's a piece of evidence. The iron came from the land and got to the ocean. There's a piece of evidence. Those same grains of iron today in the air would rust. There's a piece of evidence. The simplest explanation for why we have those banded iron formations is that 2.5 billion years ago, there wasn't any frickin' oxygen in the air. If there had been, it would have rusted. How do we know that? Because that's what it does today. So our simplest explanation, Occam's razor tells us that 2.5 billion years ago we had a low oxygen atmosphere. And we could go on, we could elaborate on that. What wasn't around 2.5 billion years ago, you might not know, but I know. There weren't any plants 2.5 billion years ago. Where does the oxygen in our atmosphere come from? It comes from photosynthesis. It comes from photosynthesizing plants. So, we can see how this fits into an even bigger story, can't we? 2.5 billion years ago, we were forming these special rocks that we don't get anymore because there was no oxygen. Eventually we evolved some plants. The plants caused there to be an oxygen in the atmosphere and no more banded iron formations. This is the way science works. A couple more things and then we're done with 1.1 here. We look for patterns. Scientists look for patterns. Evidence comes in the form of patterns a lot. How might an earth scientist look for patterns? Two examples. We could look at tree rings. Tree rings, yes. You probably know that every year a tree adds a ring of growth. And if it's a particularly dry year, all of the trees in the forest are going to have a fairly small amount of growth. If it's a very wet year, the trees will grow a lot. If there's a forest fire, the trees are all going to be burned that one year. They're all going to have char on their outside. So we can look at tree rings and we can look for annual or seasonal patterns. What if we want to look for patterns over a longer period of time? Well, we could go to Antarctica, or we could go to Greenland, where there's an ice sheet, hundreds of thousands of years of ice. That ice gets made 1 year at a time in layers. And so we can take a core, we can drill into the ice and pull out that core and look at it under a microscope, and we can see annual, yearly patterns. We can see layers of volcanic ash. And we can count the years back and say that volcano erupted in the year 963. I just made that up, but we can do that because we can see the patterns in the ice cores. Finally, scientists use models. And A model, there's a million different kinds of models. A model simply it's a way for us to simplify a complex situation into something we can understand a little bit better. And basically what we do for models is we look at causes and effects. If A causes B, we can use that as a model and say then if we have so much A, we should end up with so much B, right? So scientists use models. Right now, the models that make the news are climate models, trying to predict what's going to happen with more CO2 in the atmosphere. If we keep burning fossil fuels, what's going to happen? There's more CO2 in, what happens to global temperatures? That's all models. The more systems we understand, the more causes and effects we understand, the better our models. And the better our models, the better our predictions. So here's the way science works in a nutshell. We take evidence, such as coral bleaching, such as ocean surface temperatures and wind directions, such as banded iron formations. We look for patterns in our world around us. We combine our evidence and our patterns, and we use models to make predictions. The more parts we understand, the better our models and the better our predictions. All right, young people, I hope you got that all in your notes. We'll have a couple of days to chew on this and dig into our explorations, and we'll see you next time on our Unit 1.2 asynchronous videos. So long.